Hi, this is Phil from Simply Rhino, and today I'm going to take a look at the workflow in taking a Rhino model to a 3D print on the Formlabs Form 2 3D printer. The starting point is this existing model of a scraper, and I'm going to take a look at the various steps we need to go through in order to create a successful 3D print. The overriding principle is that the geometry needs to be built correctly in Rhino before creating the mesh STL file. Whilst it is possible to fix issues on a mesh file in Rhino, it is much easier to do this on the original NURBS geometry. In order to generate a valid STL file, the Rhino geometry for each component must be a closed volume, otherwise known as a manifold solid. What we mean by this definition is this: the outer surface or shell of the component that may be comprised of a number of joined surfaces must have no gaps or open edges between those constituent surface edges. Therefore, the outer surface describes a continuous shell creating a watertight volume. Another way of thinking about this is to consider how the part is created on the 3D printer. The part is built up gradually from a number of thin layers or slices, each of which is represented here, albeit in a simplified form, as one of these blue curves. If we take one of these blue curves and we then isolate that and look at this from above, we'll see that this is a closed curve. And of course we have a closed curve because the geometry that we've sliced through is a closed volume. If we look at this one curve in more detail, I'll try to explain the three main issues you would see when an STL file is not valid. The first and probably the most common issue is that when you have edges on the surface that are not joined together. This, of course, if we look at a slice through the model, will create a gap here in the description of the closed volume, and this will cause your STL file to fail. Bear in mind here that if you're creating a fairly small object, you may be working to an absolute modeling tolerance in Rhino of 0.001 millimeters, and so that gap doesn't need to be very big in order for the Rhino object to not join up as a closed volume. The second reason why STL files fail is that the volume may not be manifold because there will be a shard of surface or mesh inside of the main volume. In order to be a valid STL file, there should only be one manifold solid per file. And so if you have a portion of surface that may have been created by some trimming or by something that hasn't been deleted, and this sits inside the volume that you are creating, then this will cause the STL file to fail. The third reason why STL files commonly fail is by having a non-manifold edge. This, in the case of a NURBS surface down here, would be where there is a loop in the edge that self-intersects, so the surface, rather than being a continuous description, actually intersects over itself. Therefore we have a volume inside here plus the larger volume, and sometimes you may see the mesh equivalent of this, where the mesh has not built correctly and some faces have collapsed inside of the volume. Generally speaking, if you can avoid this situation down here on the NURBS volume, then you will avoid this situation on the mesh. And if you see this situation on the mesh, you can generally overcome this by remeshing at some slightly different mesh settings. The principles of good modeling practice are covered in the training courses that we run at Simply Rhino. But briefly, to check if your part is a solid, you can simply pick the component in question and then check in Object Properties, and you'll see the description of the object will tell us that in this case this is a closed solid polysurface. If the part is not described as a solid or closed surface, then the next step would be to check for any open edges using the Show Edges command. To do this, we'd pick the geometry in question, then go to Analyze, Edge Tools, and Show Edges. We'd pick the Naked Edge option here and pick a highly visible color for the edge selection, and then we'll see here our open edge. It may be just a case that you can select all the geometry in question, join together, and then the surfaces will join into a closed solid poly surface. You'll see confirmation of this in the command line, and then when you again check the objects, you'll see that Rhino tells us the total number of edges, that there is no naked edges and no non-manifold edges. If the edge analysis tool shows that there is just one or more pair of edges that are unjoined, then we may need to do a more thorough repair. It's important in this situation not to use the join edge command, as this will join edges that are out of tolerance, and in this case would most likely lead to damaged surface edges and therefore a bad object. The better workflow here would be to make sure that these two edges properly intersected with each other and then retrim the result before joining. And this may involve quite an extensive repair. So as an example of this, I would extract the surfaces that were immediately involved with this part and then isolate these. Turn off for the moment the naked edge display and then just hide for the moment these parts here. Then this area here can be untrimmed like this, and then we can show in the front portion of the surface that was not joined before, which was this, and we can check whether these two parts intersect by going to Curve, Curve from Objects, Intersection. If we don't see an intersection curve here, or we see that that surface is sticking through the back of this surface, then the suggestion would be to do something like this. We would extend or untrim this surface, then trim these surfaces with each other, then show in the rest of the middle of the E section, then retrim this part here, join this area together, and then trim and join. And then at this stage we could show edges, make sure that this area was joined, and then show in the rest of the geometry and join everything together. And we should see now that we have one closed poly surface. And if we check the edges, we'll see there's no naked edges and no non-manifold edges. When we've repaired edges in this way, it's wise to pick the object and make sure that it passes check. If you see any errors at this stage, then it's a case of exploding the geometry and finding which surfaces are seen as being troublesome, untrimming and retrimming those in turn until you have valid geometry. Once we have the Rhino geometry we're happy with, the next step is to create the STL mesh. Rather than simply exporting the Rhino data as an STL file, it's much better to create a mesh inside of Rhino that we can visualize, check, and have full control over the faceting of before then exporting this mesh as an STL file. The steps involved in creating the mesh would be as follows. Pick the geometry in question, go to the Mesh Tool tab and choose Mesh from Surface Polysurface. We're then presented with a dialog box, and rather than using the simple dialog, we'll open up the detailed controls. Here we'll have a number of different ways by which we can configure the mesh. And if a value is set to 0, this value or setting is then overridden. There are really two controls that I think are more useful than the others. So I will set density to 0 to override this, maximum angle to 0 to override this. The aspect ratio initially I'll set to 0, but I will come back to this setting in a moment. And the first setting that I want to look at is maximum distance edge to surface. And I'm going to set this initially to the same value to that which we are using in the absolute modeling tolerances in the file. In this instance, this will push the mesh facets to within 0.001 of a millimeter of my NURB surface. And we can visualize that by going to the preview setting, where we'll be able to visualize the mesh in preview. And you can see that this creates a very dense mesh. Now, if we wanted to reduce the mesh count, we can either reduce by a full decimal place. When I do this, you'll see the mesh facets are larger, or we can go up to half a decimal place, so 0.005, for example. Okay, I'll leave this at 0.001 for the moment. And the other setting I'm going to invoke here is the maximum aspect ratio. Now, the idea of this setting is that it controls the length against the width of the mesh, so that it will set a ratio for how long the mesh can be compared to the width. If you have geometry that has very subtle curvature on it, so something that is almost linear but not quite, you might see that Rhino generates very long, thin meshes. And so to counteract this, you can set the maximum aspect ratio to a value such as 3 or 4, which will mean that the mesh facets are only 3 times as long as they are wide. I'm going to uncheck pack textures, and I'm going to check simple planes. Simple planes should, given any planar faces, just build 2 triangular faces for every simple planar face, and this can reduce the mesh polygon count. The refine mesh option will create more mesh facets where Rhino encounters a seam on surfaces. I'm going to now select the OK button to generate the mesh. Now, irrespective of what layer you have active, the mesh is always going to be created on the same layer as the NURBS object. So perhaps the first useful thing to do here is to select the mesh and to create a new layer. We call this mesh, and create a sub layer, and then take the mesh and change the object layer. In this way I can now separate the mesh from the underlying NURBS. Okay, now this is a very dense mesh, and I'll probably go into this in a moment and open this out a bit, but I just wanted to go through a couple of things that we can do at this stage. First of all, if we want to visualize this mesh, there is a couple of things that we can do. We can go to Analyze, Surface, and Environment Map, and use exactly the same setting that we would use on a surface, which is Environment Map. In our display tab, we can turn off the mesh wires, and now, so that we can actually see the faceting of the mesh, I'm going to go to the arrow adjacent to the viewport title and invoke the flat shade setting. When flat shade is on, we will see the faceting of the mesh when we zoom in close, and we want to do this to make sure that we haven't got any meshes that sort of skip over some of our smaller curved surfaces. Now this mesh looks fine, it looks very smooth, but it also looks very dense, so I'm actually going to redo this mesh and relax the settings a little. Okay, so let's go back, pick the NURBS object, mesh from surface polysurface. This time I'll set the maximum distance edge to surface to 0.005, and I'll set the maximum aspect ratio to 4. I'll check simple planes and refine mesh and let the mesh build. I'll then take that mesh and push it onto my mesh layer and turn off the layer with the NURBS geometry on it. Then go to Analyze, Surface Environment Map. In Display, I'll turn off the mesh wires and then turn on Flat Shade. And we now see there is more noticeable stepping on the mesh, but that should be okay given the tolerance of our build on the machine. Next up, I need to check this mesh, and I can do that by picking the mesh geometry and running the check objects tool. Here we'll see that this is a good mesh and it doesn't generate any errors. So now what I would need to do is a couple of other things before sending this out as an STL file, and the first one of those would be to triangulate the mesh. The Rhino meshes here are a mixture of quad meshes and triangular meshes, and STL is a triangular mesh format. So I would pick the mesh and run triangulate mesh. It's probably worth rerunning the check command, and also to make sure that this mesh is closed up and solid, go to Analyze, Edge Tools and Show Edges. And there are no naked edges and no non-manifold edges. The mesh checks out as being good, and if we're happy with the visual aspects of this, then we can simply save this out as an STL file. To export this as an STL file, pick the mesh in question, go to File, Export Selected, navigate to the folder into which you want to save, choose the STL file format and give this a name, and then from the options choose the binary option, uncheck Export Open Objects and save out the file, and you'll see this saves very quickly because there is no translation going on in the saving process. What is actually saved is this exact mesh that we see in front of us. It's sometimes the case that when you create a mesh in Rhino, the result won't pass the check command. So here we have a mesh with one degenerate face. So in this case I can run the mesh repair tool, and I can check the mesh first of all, then I can choose the next button, I can pick the one degenerate face here that I want to repair, click on the repair button, and now the mesh checker reports that this is a good mesh. So you may find that the Mesh Repair Wizard will be able to fix some small issues with meshes and be able to tune up the mesh so that it creates a much better STL file. Finally, in Rhino, we'd repeat the meshing process on the other two components of the scraper housing, and then we can export these each as individual STLs and take these into the Formlabs PreForm software. So here we are inside of PreForm. I'll go to the File menu and select Open, and then navigate to the folder containing the STL files. I can bring these three files into PreForm in one go, and these will arrive in a somewhat arbitrary position. You'll see that we have a warning that there is an object outside of the build volume, and for the moment I'll ignore this warning. Next, I'll rotate and manipulate the parts so that they are inside the build volume. The base of the build volume is represented by the grid, and the remainder of the rectangular volume is represented by the wireframe box. Once the parts are inside the build volume, I'll then need to orient these into an optimum position for printing. If we now look at the parts in plan view, this is an example of how we might position the parts to optimize printing. There's a good amount of room around each of the parts, and this will propagate a good resin flow. If we look at an elevational view, you'll now see that all of the supports that need to be generated will be connected to the B surface of the product, and that the longest or tallest supports are on the wiper side of the printer. This is important and helps the build of those tall supports. With the parts in their optimized position, I can now go to Supports. I'm going to toggle off the internal support setting, which is on by default, and I'm going to accept the standard density and point size options. Next, I'm going to generate the supports. Because I don't have a particular part selected, this will generate supports for all three parts. Once these supports have been generated, I can calculate the printability of the parts. Here you can see that I have a small problem, and PreForm has reported that there are two unsupported minima detected. I can visualize the minima by turning on this switch. The term minima refers to the lowest point of the model's geometry relative to the build volume. These are areas that could fail or break off without additional support, and so to solve this problem we could either reorient the part slightly or manually add additional supports. If we need to manually add supports, we can go to the Edit All button, and we can now move around the model and add and remove supports simply by clicking on the area of the part in question or the support we wish to remove. Once we've added the necessary supports, we can then move on to the next step. Having oriented and supported the model, we can now check the slices of the build and calculate the print time. As we move around the model, we can see that the part orientation is good, thus promoting a good flow of resin during the build. The tallest supports are adjacent to the wiper side of the printer, and the parts are horizontal to the front edge. Next, it's a good idea to look at the slicing of the model so that we can quickly check the build layers. To do this, we'll use the slider on the right hand side of the screen. Starting at the bottom, we can move up through the model, and as we do so, we'll see the part slices in blue. Whilst it's not always possible to avoid islands in the slices, it's generally a good thing to aim for. As previous, we have a tick for the printability and no problems with minima or errors, and PreForm reports that the model is adequately supported. We can now calculate the build time by clicking the icon next to the print time at the bottom of the screen. Calculating the print time takes a couple of minutes, so I'll fast forward to the end of this process. Now you can see that PreForm has calculated a build time of 10 hours 20 minutes. Once the print time has been calculated, we can now send the file to print by clicking on the orange button on the left-hand side of the screen. This Start a Print button brings up a dialog box confirming the printer, resin tank and cartridge, and we can now select Send to Printer. PreForm will now generate the print files and upload the print. This takes a little time, so I'll skip to the end of this process. If we now switch our attention to the printer, you'll see that here the printer is ready to print and waiting for our file to be uploaded. Once the printer starts to receive the file, we'll see an image of the parts being uploaded and the progress of the file transfer. Once the file has uploaded, we press the Print Now button on the touchscreen, and this prompts us to check that the cartridge vent is open and the build platform is OK. And once confirmed, we press the physical button on the Form 2 to start the print. The Form 2 will now start to fill and heat, and once the target temperature has been reached, the print will start. Once the print is completed, we'll see a notification on the touchscreen. If we select the OK button, we'll have the option of sending feedback to Formlabs on the success of the print. Inside the printer, we'll see the completed parts on the build platform hanging over the resin reservoir. To remove the parts, we simply lift up the orange cover, release the catch and pull out the build platform. The next step is to wash the print, and here we will use the form wash. Here we've used a standard resin, and so the parts would be washed for 20 minutes. The cleaning solution is isopropyl alcohol, which is readily available, and the form wash has an automated system that will lift the parts out of the wash tank at the allotted time. Once the parts are washed and dried, the next step is to remove the parts from the build platform. When PreForm calculates the supports, it also creates a base around the scaffolding. This base has angled edges and quick release tabs that are automatically designed and built. These angled edges and quick release tabs make for an easy removal of the parts from the build platform. At this stage, the base and the scaffolding are still connected to the parts, and the next step would be to cure the parts. This stage is optional for standard resins, but essential for engineering resins. Here we're using standard resin, but because our aim is to create a functional, working prototype that will be assembled, disassembled and handled frequently, we are going to use the form cure. The curing process helps us maximize the performance characteristics of the resin, and in this case we will be curing at 60 degrees for 30 minutes. The final step is to remove the supports from the parts. Here you can see Steph, our Formlabs certified technician, cutting through the top of the supports with needle nose cutters. The main supports are sometimes called scaffolding, and the cross section of the scaffolding reduces where the support meets the part at an area known as the tip. In many cases, once the first few tips have been cut, the remaining supports can be broken away. As mentioned earlier on in this video, we made sure that the supports were on the B surface or inside of the parts, and, should you wish, the witness of the tips can be sanded away from the final part. Here's the final parts from the printer, and you can see that we have retained a great amount of detail. The edge logo and the handle recess have printed evenly and retained their crisp edges. These parts can now be primed and painted for a full aesthetic prototype if necessary. Thanks for watching, and please feel free to leave any comments below. If you found this video useful, please hit the like button, and remember that to keep up to date with the latest developments in Rhino for both Mac and PC, and of course the Formlabs printers and peripherals, you can subscribe to this channel. Thanks for watching, and I hope to catch up with you again in the next video.